thank you for joining us. Good morning, my name is Albatross, and I'm the design team lead for the Albatross aircraft, which is a high-altitude, unmanned aerial vehicle that provides emergency and cellular connection. Our team, Daedalus Aerospace, is comprised of 10 members. Myself, Zachary Oliveros, the design team lead, Evan Vaughn, our chief engineer. And then we're divided into 4 different sub-teams. First is the structures with cold zinc leading it, and it includes also Zachary Oliveros and Caballo Shed, that also works as a liaison with this one, and the stability and performance and control sub-team, which is also led by Olivia Bosman. Then we have the power sub-teams, which include Jonathan Crossley and Andrew Carlson. And last but not least, we have the aerodynamics team that is led by Cole Senker and has Sandra Rizet as a member. This presentation will go over the requirements and the mission performance. We will also have a summary of the 4 different sub-teams. We'll go over the cost and risk, the project management of the aircraft, and finally we'll present the conclusions and recommendations. The main objective for this presentation is to review the requirements and mission profile, then present the preliminary design review. Finally, we will detail the top 3 risks and their management to present the project management, and then we'll be seeking approval for our future tasks. Our UAV must be capable of flying and loitering at a 65,000 feet altitude. We should be able to provide connectivity through 2 antennas of cellular and internet connection, and then we will be able to withstand 2.5 G maneuver load. Now, Zachary Oliveros will talk about the statement of need of business case.
Thank you, Salma. So our statement of need, why did we design the Albatross? In the past decade or so, there's been a significant increase in not only the frequency, but intensity of natural disasters, particularly affecting communities near the equator. In the wake of a natural disaster, there are many issues that nations face. One of those being restoring cellular internet connectivity to those residents of that community. So, for example, in the event of an earthquake, if the power lines and cell towers are affected and someone is under rubble and they have their phone and they need to get in touch with emergency services, but they're unable to do so, that is a huge issue, and that poses a massive threat to the well-being of those residents of the community. That's where Albatross comes in. It will come in and provide that connectivity so that people are not in danger and that they are able to contact emergency services. So for an aircraft preview, on the left you will see our initial conceptual design at the beginning of this semester. Has a high aspect ratio wing, a T-tail, and the payload is located in front of the wing to aid with stability. On the right, you will see our preliminary design. The blue on the top of the wing, the horizontal tail, and the fuselage are all solar panels, just to note. We have maintained that high aspect ratio wing, a value of 14, and we have selected an H-tail configuration. And our payload is still mounted in front of the wing in the fuselage. So a business case. There's only a small handful of aircraft that are currently on the market that seek to achieve the same objective as Daedalus Aerospace. The first being the Zephyr S, which is $5 million per unit. And the second being the Solar 50, which is approximately $10 million per unit. We are seeking to manufacture the Albatross within a range of $1 to $1.5 million per unit. The reason why we are trying to decrease this value as much as possible is due to the nature of the financial state of many of the nations that are affected by these natural disasters. Now, these nations themselves would not probably purchase our aircraft, but they would contract through a cellular company to offer the service. That cost for the nation would likely be lower, with a lower operating cost for the aircraft, hence the $1.2 million. And it is also important to note that for the Solar 50, they experienced some issues during testing and it did crash. So they're doing some re-engineering and redesigning, which leaves a gap in this niche market for Albatross to step into. And I will now hand it off to Evan Vaughn, our chief engineer, to discuss mission performance.
Thank you, Zach. To start off mission performance, I'm going to touch on our concept of operations or CONOPS for this aircraft. First, it will be launched, connected to 2 weather balloons, where it will be carried up to 70,000 feet. At this point, it will detach and then cruise down to its loiter altitude of 65,000 feet. It will then provide connectivity to the disaster zone below and begin its holding pattern, which is a 25-mile radius about the disaster point. It will then remain there for about a week. At this point, ground services were commanded to come back and will descend and then reach the landing point where it will be controlled by a pilot and landed into a net. So to achieve this, we need some ground support. The main items of ground support are going to be transportation of the aircraft and its trailer box to the location where it will be deployed. It needs to be assembled, which is a simple process of sliding the empennage booms into the wing clamps, as well as sliding the fuselage track inside the fuselage, which has the components balloons inside of it. We then need to fill the helium balloons and launch the aircraft. We also need to have a net a week later for it to be landed on, as well as a pilot standing by. And then we also need a team to prepare it for relaunch once it is landed for inspection to ensure it's still airworthy. So this aircraft does also need some communication systems to fulfill the requirements. The aircraft is carrying a 1.1 pound transmitter CPU. That is our payload. That is what will connect to the satellite connection system, as well as beaming down the connection down to the people on the ground. Our task was to design the aircraft to carry this payload and to house it, not to design the payload systems itself. So that's the scope of our project is in the red bubble. It's the aircraft itself. To achieve this task, we need some electronic systems. The main three are shown here. We need a battery pack. This is made up of 3 lithium-air battery modules. This will give us enough power to maintain loiter altitude, as well as potentially ascend and for descent and for landing. We also have a control computer, which includes a Navio 2 and a Raspberry Pi 2 to ensure that we can be stable and we can trim at a 25-mile radius around our point. And it also houses a transmitter CPU, which is our payload, to give cell phone reception and relay between the satellite network and the ground network. We also have a propulsion system, which is our brushless motor and our propeller to ensure that we have enough power to maintain cruise. I'm also going to touch on our constraint analysis and give you a brief overview of how we designed our aircraft. First, we had to develop a design space, which can be seen here in the green region. This is a feasible region designed for this aircraft. The 2 vertical lines, as you see, these are structural limits. The blue line is not an active constraint, that is our landing constraint for wing loading. The orange one, however, is. That's our cruise wing loading. And that value was developed from a typical sailplane value of 0.525 pounds per square foot with a factor of safety of 1.25 applied. That yielded a value of 0.42 pounds per square foot for wing loading and cruise. The other value that is horizontal, that is a power loading constraint, that is a technological value. It's a technological constraint based on battery technology as well as solar panel technology available. We came up with a value of 0.0155 horsepower per pound of the power system we can produce. The other 2 lines that are not linear, they are the cruise line and the sea level maneuver line. The cruise line is the blue one. This was developed using a drag coefficient of 0.089, as well as our CL value of 1.5, and a load factor of 1.1. This is to account for a potential bank due to create our 25-mile radius about a fixed point on the ground. The sea level maneuver load, that was using CL max instead of CL trim, and using sea level density to estimate the largest load that this aircraft will experience, as well as incorporating the 2.5 G load factor required by the RFP. Using this design space, we developed an aircraft design point, which can be seen here as a black dot. This black dot corresponds to a value of weight of 57.5 pounds and a planned form of 137.2 square feet. This gives us a wing loading and cruise of 0.419 pounds per square foot. We do realize that this is very close to our constraining line of 0.42 pounds per square foot, but this was an intentional decision, as that value was a very, very conservative estimate, as it was used for sailplanes, which are for manned flight and are typically much heavier than this aircraft. And it also has a factor of safety applied. And we also wanted to make sure we could give ourselves enough weight to ensure structural integrity of our aircraft, using our low density, high strength materials. Here you can see our power required of 0.6 horsepower. That was an estimate that is on overestimate as well, to give us more power in our batteries and more power in our motor in case we need to loiter for longer, or in case we potentially need to ascend by ourselves and for descent as well. And that corresponded to a power to weight ratio of 0.0104 horsepower per pound. Next, I'm going to pass it off to Santa Rosa for wing design.
A little more about wing design here. So basically the wing design to reach and operate at 65,000 feet. The airfoil selected was L1003M, and that letter M there stands for modified version of that airfoil. As you can see on the picture on your right, that dashed line at the tail is a deflected line. It's not a flat. That's to reduce the drag coefficient. The estimated CL max for a 2D design is 2.2, whereas the estimated 3D lift coefficient is 1.9. And that is derived using taking into account the very low density at the altitude of 65,000 feet. And with the required wing loading of 0.419 pounds per square foot, with the landform area of 137 square feet. On that picture on bottom, you can see that it's a rectangular wing design. The reason for that is that we're trying to get the most lift possible out of our wing. Therefore, we have no leading edge sweep angle, and taper ratio of 1 and aspect ratio of 14. The wingspan is 43.8 feet, with the chord length of 3.13 feet, and with the max thickness of 0.6 feet. So the wind tunnel testing is subject for next semester to support all of these values. And here's the graph of a 2D and 3D lift curve, the graphical representation of how we got these values. And I'm going to hand this off to Kivade.
Thank you, Sandra. I'll be going over empennage and control surface sizing. So for our vertical tail, we decided to use a NACA 0009 airfoil. The reason this was done is because it is a thin airfoil, which means it generates minimum drag, and it is also a symmetrical airfoil, which means that it will produce no unpredictable forces from the empennage until and unless a control surface has been excited. Our volume coefficient for our vertical tail was 0.0134. The typical range for most vertical tail volume coefficients is anywhere between 0.02 to 0.05. The reason our vertical tail sits outside of this range just marginally is because our aircraft's environment of operation and mission parameters are so different when compared to other aircraft. We also chose to introduce leading edge sweep of 11.3 degrees. This was done to move the aerodynamic center aft and give us a longer moment arm and give us more control authority. We chose to have a rudder height of 1.75 feet and a rudder chord of 0.75 feet. For a horizontal tail, you can see that our antennas are attached to the horizontal tail. We have one on the upper surface and one on the lower surface. As mentioned before, we have a H-tail configuration, so the antenna on the lower surface should not affect our stability parameters much because it does not see any clean flow of air. Not only is it shielded on either side by a vertical tail, but it lies within the region of propeller wash. And the antenna on the upper surface actually aids us in stability, increasing our lateral stability, and acts as a third vertical tail. For our horizontal tail, we have a volume coefficient of 0.2389. The typical range lies between 0.3 to 0.6, and the reason the horizontal tail lies outside this range is the same as the reasons I've mentioned before. For the horizontal tail, we chose to have no taper or no sweep and went with a simple rectangular wing. Our elevator chord is 0.6 feet, and our elevator span is 6 feet. This is our entire empennage rendering. As you can see, the H-tail configuration, the solar panels on the horizontal tail, and you may also notice the two elbows at the bottom of our vertical tail. That's where the empennage mates with the booms for the aircraft. This is a cloud plot showing aileron chord over wing chord versus aileron span over wingspan, and the green range in the middle of the graph represents an area where the ailerons have been sufficiently sized. And you can see data points from multiple aircraft, and as you can see, the Albatross data point lies within the green range, telling us that our ailerons have been sufficiently sized. And next, I would like to hand it over to Coach Zinker to talk about aircraft performance.
Thank you, Kev. Morning, everybody. Now that we've covered the design of our aircraft and the lifting surfaces, we'd like to go over performance of that design and how it stacked up against our mission requirements. If you'll recall, our mission requirements were to fly at an altitude of 65,000 feet for up to and above a week. From that, we got some derived requirements from our design space that was described in the constraint analysis, which gave us values for our takeoff weight, trim velocity, and wing load. Using those values and conducting performance analysis, we've plotted a Venn diagram to show that we can produce enough lift at 65,000 feet to perform a 1.33 G maneuver, which means at a load factor of 1 for steady level cruise, where the blue diamond is indicated, we're well below the solid black stall line at 65,000 feet. For that lift, we do increase a drag penalty that totals to 3.42 pounds. Because we're operating at such a high altitude with low density, we are flying at a pretty high CL value, about 1.5 in trim, which is represented by the red star in the graph to your right. That value does correspond to a substantial amount of induced drag, 0.65 or 0.065, which when combined with skin friction and pressure estimates, gives us a total CD value of 0.89. That drag value, although slightly higher than minimum drag, does still give us a minimum power required value at 65,000 feet, which is indicated by the power required, power available plot on the right there. The solid black line representing power required at 65,000 feet, and the blue diamond representing our trim point. We end up with 0.348 horsepower required at that altitude, which when compared with our 0.6 horsepower available that was described in the design space, gives us plenty of excess power to climb at that altitude. To describe that, we have contours of piece of S in feet per minute of climb displayed here. And the two most important points in this graph I'd like to point out to you are our service ceilings and absolute ceilings. If you'll recall, we had a mission requirement for a service ceiling of 65,000 feet, and we've well exceeded that with a service ceiling of 71,000 feet, indicated by the contour of 100 feet per minute. Our absolute ceiling was 86,000 feet, which does give us the ability to climb over any turbulent weather or unexpected atmospheric anomalies. A quick summary of our performance. We were able to produce enough lift so that we do not stall in our cruise condition, as well as giving us a very slow landing velocity so that we can safely land our plane in a net. Our flight envelope exceeded requirements, and our endurance indicators let us know that we have about a 200-mile glide range in the event of an accident. With that, I'll turn it back over to Sanjay Rizaev for ascent and landing.
So the other two important stages of our mission are ascending and landing. So first I'm going to talk about ascending. Basically the mission is planned to be ascended by 2 weather balloons filled with helium. And the total volume of 2 balloons filled with helium should be around 1,500 cubic feet and producing overall a buoyant force of 60 pounds. So the balloon is able to reach a bursting altitude of 75,000 feet, but once we reach an altitude of 70,000 feet, we're basically going to detach from the balloon, descend down to our loitering altitude, and continue our mission from there. And the duration of the ascent is estimated to be around 42 minutes. And then the final stage of the operation is the landing, and it's a net landing with the speed of 16 feet per second. It's going to be gently stalling above the net and descending down into it and be wrapped around by that net. And the advantage of using such a method is that we can pretty much land at any terrain, including boats, as you can see on the picture. It also reduces the complexity of our aircraft assembly. And another aspect to it is due to our weight restrictions, we couldn't go with conventional method of having a landing gear. Therefore, we decided to go with a net landing. And with this, I'm going to turn this to Olivia.
Thank you, Sandra. We'll be talking about weight balance. So as you can see in this table, this is the weight breakup of our aircraft from structures to payload to control systems, and as well as power. The requirement for our aircraft is that it must weigh less than 4,000 pounds. As you can see, our current total aircraft weight is 57.5 pounds. The reason for this big gap in the requirement to our actual weight is because the requirement was based off of old battery technology. However, we were going with new experimental battery technology that allows us to condense the size of the batteries as well as the weight of the batteries while having enough power for our aircraft. For our XCG and ZCG locations, they were measured from the interface between the nose cone and the fuselage and from the center line of the fuselage. So our ZCG is -0.503 feet and our XCG is 4.646 feet. And our aerodynamic center of the aircraft is 5.349 feet. I'll also be talking about static stability. So our aircraft must be longitudinally, laterally, and directionally stable. And as you can see from this table, our aircraft meets all those requirements. So our static margin, which is calculated from our XCG and XAC, is positive at 22%, and meaning that it's stable. And then our CM beta, which is our directional static stability derivative, is positive, which means that it's stable and fulfills our requirement. And then our CM alpha and CL beta, which are our longitudinal and lateral static stability derivatives, they are both negative, which means that our aircraft is stable and meets the requirements. Now I'll be passing it off to Andrew Carlson.
Thank you, Olivia. So I'll be talking about the propulsion system requirements. So our requirements for the propulsion system are that we need to cruise at 56 feet per second, which is 33.2 knots. We must also be able to counteract the drag force given to us from the aerodynamics team of 3.42 pounds. We also limited ourselves to simplify construction of a fixed pitch propeller, as well as optimizing that propeller for a cruise condition. So the motor selection criteria went as follows. We were given a 0.6 horsepower power output from the aerodynamics team, and from there we needed to find a motor that provided the 0.6 horsepower at a 30% throttle setting, and it must also be of high quality construction where we can operate in a large temperature range that we will experience at 65,000 feet of negative 60 degrees Celsius to positive 55 degrees Celsius. So the motor that was chosen is the Turnigy SK3 fan drive. It's a 1600 kV motor with a rated power output of 2.25 horsepower, which gives us a 30% throttle setting of 0.675 horsepower, which gives us a little bit of wiggle room for losses in gearbox efficiencies as well as propeller efficiencies. The 30% throttle voltage will be at 7.8 volts, and the operating RPM will be at 12,480 revolutions per minute. So the propeller requirements are that we need to counteract the drag of 3.42 pounds, and we must not exceed a propeller diameter of 4 feet to avoid interference between the booms. And we must be able to operate not only at 65,000 feet in our cruise condition, but we must also be able to operate at sea level to allow for maneuvering as well as a go-around during failed landings. So the airfoil that was chosen for the propeller is the LS0417, which was chosen for its non-violent stall characteristics as well as its thick profile. We'll be able to have a 0.6-inch thick propeller along the route, as well as be able to provide a coefficient of lift of 1.6 at 19 degrees angle of attack. So the propeller design, we maximized the diameter at 4 feet and incorporated a root chord of 3.5 inches, with a taper ratio of 0.3. This gives us a pitch value, a geometric pitch value of 3.5 feet per revolution at a propeller efficiency of 80.2%. So at these cruise values, we get an advanced ratio of 0.64 and a propeller optimum RPM of 1,313 revolutions per minute. So to mate the high revolutions per minute motor with the low RPM propeller, we needed to incorporate a gearbox, which we found needed to be a gear ratio of 9.5 to 1. And next I'll hand it over to Jonathan Crossley, Power Systems.
Thank you, Andrew. So the requirements for the power systems is to be able to provide internet and cellular connectivity and also power the aircraft systems via batteries and solar panels. To provide that connectivity, we'll be using long periodic dipole array antennas with a 100-watt power consumption. We'll have 2 of these antennas, one providing satellite communication and one providing ground communication. Those will be located on the upper and lower surfaces of the horizontal tail. This is a general layout of the power systems. We have 3 battery modules, each having a configuration of 10S1P, which means 10 cells in series. Those 3 modules will be connected in parallel and managed by a battery management system and charged by solar panels. That system will power the 5 main aircraft systems that you see here. Those 5 main systems, we calculated their power consumption at the cruise condition with some assumed duty cycles and conservative efficiencies. For 14 hours of nighttime operation, we'll require at least 10.6 kilowatt hour battery capacity. And as you can see, the motor is the largest power draw of the systems. With respect to the batteries, current battery technology wasn't able to meet our energy density requirements. So we decided to go with a less mature battery chemistry. We decided lithium air has about a technology readiness level of 3 to 4, meaning the concept of the chemistry has been proven, but is still in the laboratory phase. With that, and the 3 modules, we were able to get an energy capacity of 19.8 kilowatt hours. The unique thing about this chemistry is that the anode and cathode can be made to any shape that we desire. Those batteries will be located in the forwardmost position of the fuselage to aid in stability. powering those batteries and the aircraft systems during the day will be solar panels that are triple junction gallium arsenide solar cells, which are some of the most efficient currently available on the market. They are also proven in the space industry. Those will be located on the upper surfaces of the fuselage, wing, and horizontal tail. Now I'll hand it over to Cole Zink.
Thank you, Jonathan. So for our structures requirements, we need to withstand a 2.5 G maneuver load. We need to fit within a trailer box. We need to weigh less than 4,000 pounds. And we need to operate from the temperatures of -60 degrees C to +55 degrees C. To start out, we used a elliptical lift distribution and trapezoidal lift distribution and averaged both of those to create our max bending moment for the aircraft that will help us with the max tensile strength and or max tensile stress and max compressive stress. Here's a span-wise shear and moment diagram. This will help us in calculating the shear and the moment that the center rib will endure during a normal cruise. Here's some structural analysis for our aircraft. So we need to withstand that 2.5 G maneuver load. So our max tensile stress is 12 KSI. Our max compressive stress is 6.2 KSI. And so we went with a hollow cylinder design that will help us, that got us the lowest weight possible for our spar and gave us the lowest wingtip deflection that we were looking for at cruise. So our max wingtip deflection at cruise would be 3.5 inches. The material of our aircraft, the spars, ribs, fuselage, and clamps will all be Hextel IM712K carbon fiber pre-preg. This will be this was chosen over other materials such as aluminum and fiberglass because of its low density. The skin of our aircraft will be a mylar polyester film, and the nuts and bolts connecting the fuselage to the center rib and the booms to our main wing will be stainless steel. So our ribs for our aircraft will be our airfoil, which will be our L1003M, and then our spacing will be 21.6 inches, which is we looked at similar aircraft such as sailplanes and gliders to get this number. So some thicknesses of our components, our rib thickness will be 1/8 of an inch thick. That will help us with shear flow. Our skin thickness will be 5/1000 of an inch to help with torsion. Our spar thickness will be 1/4 of an inch. That will help us with bending and the moment and the deflection of our wingtips. And our spacing will be 21.6 inches to help with skin buckling. Some general dimensions of our aircraft: we will have a 43.8 foot wingspan. Our ailerons are at the outermost point to help with, to get the most control authority possible. And our elevator is 6 feet to give us the most control authority as well. The diameter of our fuselage is 0.583 feet. That has given us the most volume possible for the least drag penalty. Our fuselage length was chosen to help move our CG forward and to help and aid in stability. Our boom length was also chosen to get our empennage into clean air so they have the most control authority during cruise. Now I'll hand it over to Zachary Albatross to go over project management and cost.
Thank you, Cole. So to delve into these materials a little bit more and quantify exactly how much this is going to cost, we have a breakdown here. The material that is most commonly used on our aircraft is carbon fiber, as Cole previously mentioned. The wing alone is estimated to be about $54,000 in carbon fiber. By far, though, the most expensive component of our aircraft are the solar panels with about 150 square feet, and that equates to about $520,000 just for our solar panels. And then our battery pack is expected to be about $20,000. When you add up all of these costs, the total material cost is estimated to be approximately $600,000. So throughout the semester, every team member was required to record the hours that they devoted to this project and specifically which categories they devoted their time to. So for example, with technical, you can see we have quite a few hours, 981. That relates to CATIA, all the time we put into our CAD models and so on and so forth, and calculations. The total hour count is about 2,117 hours for this semester, equating to approximately $200,000 for labor this semester among our whole team. Projected labor costs. So this project does extend into the fall semester. It is a full year. So we did have to estimate what this entire project will cost. As you can see here, we did not do a direct correlation between spring and fall, because next semester we are going to be manufacturing and doing some tests, and that is going to provide a bit of a learning curve for some of us, considering we don't all have manufacturing experience. So under advisement from a professor, I factored in an addition of 1.5. So assuming that, we would have an increase to 3,176 expected hours in the fall, resulting in a total project cost for labor of approximately $500,000. So a program plan, just to give you a snapshot of everything we've done this semester. Started the program, presented our system requirements to our professor to ensure that we were on the same page, negotiated some of those requirements from our initial requirements. Our concept design review, where we presented 3 different options, one of which you saw at the beginning of the presentation. We had our interim design review, where we provided further details. Then we had our technical data package, or TDP, where we presented over 95 technical drawings of our aircraft. We're currently in the preliminary design review, and next week we will be submitting our final technical report to our professors to wrap up this semester. And I will now hand it back over to Salma for conclusions and recommendations.
Thank you, Sam. As you can see, the aircraft has been predicted to fulfill the requirements stated at the RFP. The one that might seem a little bit concerning is the size one, but because we have unfastenable booms, we should be able to still fit within the size requirements. However, after some testing is done, Daedalus Aerospace has chosen the top 3 risks that we might encounter. The first one is having an underperforming airfoil. This means that if the CO max changes in around 10% from its predicted value, we would have an aircraft that could potentially not reach the loiter altitude requirements. Therefore, we would just use the best performing second airfoil that we have on the decision matrix and recalculate all the parameters. Our second risk would be underestimating the wake effects that could potentially give us an uncontrollable aircraft. However, to prevent this from happening, we would just add a trip strip to the wing and potentially move the empennage to mitigate this. And finally, if we overestimate the pilot's ability to control our aircraft in different weather conditions, they could potentially crash or cause structural damage to our aircraft. That's why the pilot will undergo a landing training before they actually can pilot it. As you can see, these are the probability and the consequences of our risks. Wake effects is by far the highest of our risks, but because we have an effective mitigation plan in place, we should be able to still perform as predicted. Because of our budget and time constraints, our aircraft cannot be scaled down, nor a wind tunnel model can be done. That's why we are recommending to create and follow 3 different plans to verify the parameters of our aircraft. The first one would be to build a wing section of our aircraft and wind tunnel test it to show that our parameters are still correct. The second one would be to power our systems and run it for 24 hours to show that we can stay aloft during day and night. And finally, we would subject our wing section to structural loads that it will experience during flight to prove its structural integrity. In conclusion, our aircraft should be able to fulfill all the RFP requirements. I will create and follow 3 different test plans to prove that it can still perform as predicted. Daedalus Aerospace is thankful to all the faculty members that contributed into aiding in the performance of this aircraft. Thank you for your attention. Do we have any questions?
Yeah, go ahead. Paul, I was just going to say, let's go ahead and open it up.
I'd like to compliment all of you. This presentation is amazingly technically dense. You covered a lot of ground and considered a lot of things. And I'll be honest with you, I have trouble keeping up sometimes. First of all, want to talk to you about one of the constraints, which is the power constraint on a couple of points. The capacity of the batteries and the capabilities of the solar panels. Under what environmental conditions, specifically what temperatures were those evaluated at?
So the solar panels are being used on the International Space Station, so they can go down to cryogenic temperatures. As for the batteries, because they are still in a laboratory phase, they're still discovering what temperature ranges they can operate in.
Okay. And if I could pull on that thread, the efficiency of the solar cells is quite impressive. Is that a nominal, or is that at the range of environmental temperatures that you're spec to?
I do not know the exact temperature that they used during the test standard, but it was at the 1.5 suns, which is sea level, and they accomplished that a couple months ago at that efficiency.
Okay. One comment I have on slide, the weight table for the weight of your vehicle, whichever slide that is. That's going to be slide 36. Did I just miss it? Where are the antennas in this?
That falls under the power system.
Yes, so there.
Okay.
This is just an overall breakup of our weight. So our power includes the batteries, it includes the antennas, and it includes the solar panels.
And the breakups are provided for you in the appendix.
Okay. Okay. Where are the weight for the harnessing? Where is that allocated here?
It's also allocated for the harnessing for the actual power system.
Harnessing for everything.
Okay, so that's connected to a mounting track, so that would go under fuselage structure.
Okay. Okay, thank you. And as far as you mentioned that in January you had a requirements review?
Yes.
Just a comment, it would have been good to mention up front that all the requirements and the allocation thereof were vetted, because I kept writing where did this come from? How is this derived? And if there's reference material that, or at least building confidence that they had already been vetted.
So to clarify, you'd like elaboration on where those requirements, how those requirements were derived, not just listing them?
Yes.
Okay.
Yeah, but just even that there was a requirements review.
Okay.
And referring folks back, because you moved with lightning speed through the requirements, and I think it would have spending a little time recapping that would have been valuable.
Okay, I apologize for that. That was probably my mistake.
I have other questions. I could probably keep talking for the next 20 minutes, but I'll let somebody else have an opportunity.
So what I'd like to do is just kind of limit everybody to 3, and then once we get done with the 3, let's get around and come back to you. How about
Right.
that? All right, so 3 questions, pick your top 3, and let's see if we can get back to Paul. All right.
Right.
So go ahead.
What are the trade-offs of cruising at, say, 65,000 feet or, say, 10 or 20?
So for 10 to 20,000 feet, you could still expect weather, and also there's more air traffic. Since our aircraft is going to be operational autonomously for that week duration, we would prefer that it stays at 65,000 feet, so that it does not. There aren't any effects with other aircraft. Also, it was part of the initial requirements provided by our professor.
So I want to keep the questions to the panelists first, and then if we have enough time, then we can ask for open questions from the audience.
Okay.
All right, thanks.
So,
Okay.
first of all, that was another great presentation. I always love watching Professor Zwick's groups. They're very requirements heavy, very relevant to what we're doing in the industry. There are a couple things that caught my eye, though. One of them was, can you go to slide 34? So for stuff that's like net recovered, or, I think in situ has something that applies to the book or something like that. The maneuvering load, the 2.5 Gs isn't normally the design driving load function, it's the landing into the net or whatever you're flying into. And I think you said it's generally going to stall, but just put it into perspective, 16 feet per second is not gentle. An Air Force jet, a really hard landing is about 10 feet per second. So that's going to be, I was a little surprised that wasn't your design load condition, or that wasn't at least, was that
We'll consider it for next semester.
Okay, that'd be great. Another quick thing for your flight envelope, so you have pretty big wing, but I didn't see anything related to gusts. So I went with that. And then last thing on slide 62. So so this is your calculated stresses?
Yes.
Okay, so I don't see any material properties. I don't know how much margin do I have to yield, how well is the trigger holding up. Yeah, so that would be good to show, how much margin you have to yield your material properties. But that's pretty much all I got. You guys did a great job.
Thank you. Appreciate it.
Yeah, it's every time I come to these, I learn more and more from you guys. Get more and more impressed on that. I love the fact the way you gave the compelling case for the product, and also the way you developed the design space. That was pretty freaking good, actually, because a lot of users just jump in, just okay, we're gonna make this. You guys actually define, here's the boundaries of the configuration. I mean, you made it so even I could understand it. Perfect. These other are gonna be just nitpicky, but I probably would have recommended the legitimate schedule that you had, put that in front. It kind of tells us where you are. And then you can repeat it again later, but that way we know exactly what's going on. From some of the details, there was just some small ones that I couldn't quite understand, like where the wing design, where you got the little kick on the back and then you're kicking up the front. It was not much detail that I'm not quite sure where you're heading. Along the lines of what Bryce said, this thing's gonna be ultra light. I would have loved to see more densities and stuff because I still can't see you getting to that weight. I mean, that thing's huge. It's gonna be very big. So you're gonna have to worry about the dust and flutter on that thing. You might have to take some kind of a look. And then the other thing would be the solar panels. Are you talking about like the forming type?
Yes,
A
the
little more
solar.
detail on that, because most people think like solar panels on the roofs, there's no way in hell you can do that.
The solar cells are less than 40, I think it's microns,
Yeah.
and they're very flexible, so they would be able to conform to the shape.
But it's kind of like along the lines of what Paul was asking, these other little details, it's almost like that weight you're trying to hit is really tight, and there's a lot of stuff going on in there. So just a little more detail, break it down some more, because we kind of see that as a big risk. Aside from the landing, that's the other one we're kind of down into. Is that wingspan landing on those things? If it really doesn't, stall and drop gently, you're gonna break something. But that's all I got. Nice job.
Thank you.
Good job, presentation, very informative, well put together. 3 quick things, the solar panels again, mounting them on there, so that, I would go into a little more detail how you actually plan on attaching that, because that's a lot of area. I mean, if you're gluing them on, even that amount of area is gonna create a significant amount of weight of just your adhesive. So, devil's in the details, a lot of things like this. So, look at that for next semester. Your antenna location, I was a little concerned maybe on the bottom one, you might be blocking some of your pattern between your booms. So you might look at what effects your fuselage will have on its perception. And then on your mass properties, stability. Was it a requirement that you had to have a stable airframe, or was there an option where you could actually go with an unstable airframe and get a lot more performance out of something like that? Was that a constraint that it had to be stable?
So that was a derived requirement, flying at 65,000 feet and then trying to stay in a 25-mile circling radius. We wanted that stability so that we could actually achieve that instead of, since our aircraft is so light, then maybe if there's a gust or something like that, then we can actually recover from that and then come back into the mission profile and continue with it.
If you make your airframe more or less stable, it becomes more maneuverable, lower drag, trim, just something to consider.
Thank you.
Thanks.
Awesome. All right, you guys put in a huge amount of work and you covered a substantial amount of ground. One thing that I really like, it's always exciting for me to see risk assessments. So thank you for talking about that. Let's talk more about risk assessment. So
TRL level 3 or 4 on batteries, holy cow, that's a huge risk. So I'm curious why, on slide 76, why that wasn't identified as a giant risk.
This is because with the other research that we did in previous aircrafts, they use a lot of experimental technology in their materials, even in their motors. So we basically decided that instead of doing that for all our entire aircraft, we would just go with the batteries. So that way, I know it does present a risk, but we just decided that and we discussed it with our professors so that we could go forward with it.
Okay, yeah, so think, if you look at a little bit about the definitions of some of the TRLs, I think it's usually like TRL 7 or so is about the time that we usually are ready for flight test. You can maybe get a little bit short of that, especially with the battery. It's just maybe a limited flight time or something, but that's a huge risk. So I would recommend identifying that one. And kind of piggybacking on that, what happens to your aircraft and your design and your company if the batteries aren't ready?
It doesn't reach 65,000 feet.
Right, well, actually, it probably would, because the balloons will get it there.
It wouldn't stay there.
We
We're relying on that
sure
climb
it'll stay
ratio.
there.
Yeah.
So,
They have to cycle
my question is, because you have to deal with reality, what is your fallback?
Yeah, if you
That, there are other battery technologies that are a little less dense and power dense, but we could also still operate this aircraft for a week, but we would have to limit where we could operate it. They'll be based on solar radiance values and daylight hours so that we can charge those batteries and how much we can actually run just off the solar panels, whether or not they can run for 24 hours.
That's a really great point. I'm glad.
And to build off of that, in the appendix, we did provide you with a graph of solar radiance so that you can see how much sunlight we are expecting.
There's a plot there, yeah. Those are based off of ground level values. So it's conservative, and as long as you're above that line for solar radiance for the period of time in hours on the x-axis, you can operate that aircraft for 24 hours.
Great job looking at that. So, kind of the takeaway that I'm trying to get at is it's fine to accept big risks, but you need to think about the fallback plan when that doesn't come to fruition the way things sometimes don't. And I know battery development is one of those, like you're on the absolute cutting edge of what technology can do on planet Earth right now. So, question as far as voting control on slide 39. And I know mine are taking a little longer, so I'll be on the stage after this. So, it's great to see that the requirements are met. I was hoping for more. Do you have plots that talk about CM naught, CL naught, CM naught?
We do not. We have done calculations for our CM trim, and we wanted that to be 0. So that's why I don't know if any of you caught it or remember it, but it was alpha trim of 11 degrees, and then our incidence angles of our wing and horizontal tail are both 0 degrees, so that we could get that 0 value for CM trim. But other than that, we do not have that.
Okay, yeah. So a little bit more substantiating data would have really helped me, even if it was in the backup slides. I understand that your presentation was packed. So maybe can you talk a little bit about how you size the horizontal and vertical tails?
Well, one of the main restrictions that we had when we were sizing the empennage was figuring out how to deal with propeller wash, because we chose a pusher configuration instead of a puller configuration. So we had to, the height of the vertical tail was dictated by the cone of prop wash that the propeller would shed.
Sure.
So
can you go to 37 while he's talking? Thanks.
Yeah, so we had to size the vertical tails to be high enough to be outside prop wash, and also the horizontal tail and the elevator is sized in such a way to help us cancel out the moment from our wing, because our wing generates a pretty large moment.
Sure. Okay. So I think you just kind of hit on the important point, because a lot of the sizing, especially with the horizontal tail, is based on the stability. Having the plot where you can start to look at horizontal tail area and that sort of thing, that starts to really substantiate and really helps me convince me that your design makes sense. So please, add a little bit more on that. One kind of point is it looks like your big antenna is in the prop wash, especially the lower antenna. think a little bit about the swirl, and there's just a lot of buffet that you're probably gonna get on that antenna. And your structure is already pretty sparse, so fatigue is probably gonna be a really big problem with that antenna. You may choose to not put it there for that reason. So, but, you know, you guys did a huge amount of work, so thank you again.
Thank you.
Thank you.
Okay, so we're gonna go back to Paul, you have others?
Yes, yeah. With regards, there is a requirement, it's an implicit requirement that fit within a 53 by 7.2 trailer box, and it said that it's going to be assembled in the field. What consideration was given to the design and analysis of those interfaces, and where are those interfaces?
Okay, I can talk to that, and this picture is actually perfect to see that. Do you see the booms here, the two holes in those? There are 2 half-inch bolts that slide into those places, and there's a clamp in there that it slides into to hold it in place. And that's connected into the wing rib, which is a thicker reinforced rib at that point. The other thing that needs to be put in, as you can actually see here, a track just behind the batteries is slid in and fastened into place. That's the only assembly that's needed. It's only putting together 4 bolts and nuts and then sliding and fastening that in. So it's very simple to put together, and it should be a very strong interface from the sizing that we did for that.
Yeah, an explorer would be probably good.
Okay.
And I mean, and thinking of the challenges, particularly with landing, I concur that net landings are very problematic. It's implicit, although it's not explicitly stated. Is reuse a requirement for this system? Does it have to be completely reusable? Is that a requirement, or is that something?
Yes.
How does that fit into your business case?
Sure, so for our business case, if you want to go back to the business case and show the other aircraft. So the other 2 that for the cheapest task, that's per unit price. That's $5 million is for the closest one. Ours is 1.2 per unit. The idea behind that is the Zephyr achieved, I believe, it was 32 days aloft. But with our aircraft, we can achieve a week aloft, but you can have 2 of them for less than half the price of the Zephyr. So you can service one while it's down, and then relaunch it once the other one needs to come down and be inspected. That gives us a week as well to repair whatever needs to be repaired, rather than just leaving it up there with all these fatigue cracks and having catastrophic failure. We can catch that. And that's the business case behind having 2 and being able to be aloft indefinitely.
Okay.
Yeah. It's a lot of redundancy.
So somebody else?
Dr. Ashworth, or Dr. Ashworth?
Good job.
Thank you.
Oh, I'll ask a couple. Did you analyze the drop from the balloon?
Yes, so we did look into that. So we have a servo that's mounted to the center rib. I don't know what picture might show that well, but basically at the center. It is mounted after the CG slightly, so that as it is lifting up, the aircraft is already in a pitch down attitude. So when it is released, it will go descend down to 65,000 feet.
I'm worried about the recovery. You've got a super stable, 22% stable vehicle.
Yes.
Did you size for the recovery at 2.5 Gs, because you're going to be running on your max structural limit to keep that airplane from descending down to 50,000 feet, because you're dropping it at a speed well below stall, you're dropping it in a stalled condition, and you need to recover it. So make sure you analyze that in detail. I think that will drag you to a 6% static margin, if not less.
Yes, so we were actually going to consider for next semester reviewing these parameters, because we do know that they are they are exceptionally stable, and then we can come back on them a little bit. We just wanted to freeze the design for now and present on it now. But yes, we have thought about that, and we're going to be looking at it next semester.
We already know you're fly-by-wire, right? So take advantage of that. And you talked about pilot training?
Yes, so.
Yeah, I don't think that's gonna happen. I don't think anybody will ever be in the loop with this vehicle. I think you're gonna have to just deal with it being autonomous. Except for maybe a high-level command, I want you to land here.
Yeah, that is exactly what we're planning on doing,
That's
just
what,
for,
yeah.
yeah, just for being able to like install it above the net. So that's basically all the pilot would be doing.
Then that will destroy the vehicle.
Yeah.
I'm sorry to say, but I would advise just skid landing. You're going 16 feet per second, that's not straight down. You're going 16 feet per second across the ground. Your vertical rate of descent, because of your wing loading, is gonna be so small. You should be able to take that load much easier if designed. And you're gonna have some really big wing bend if you still have the
Yeah, can I pile on
Go for it.
So wing bending. Hey, do you guys think or try to account for the loss of lift because of wing bending? Because, I mean, your wings are gonna be substantially less efficient when they're kind of curved up like that.
We did calculate dihedral at cruise condition. Cole Zink talked about that in his slide with wing spar deflection. And with his method, we calculated that it was 3.5-inch deflection at cruise with a 43 wingtip deflection at cruise.
3 inches at 42 feet?
Yes, that's why we decided that was negligible.
Not at 42 feet, half the wingspan.
Half the wingspan.
So approximately 21.
Yeah.
That's,
so it's perfect.
is that, how comfortable do you feel with that assumption based on the stiffness that you're planning?
Very comfortable. The material that we're using is, the physical properties of it are crazy. So, it's the thickness that we have on it, I have total faith in that.
Okay, all right. And then one question on requirements, 25 nautical mile radius. Cell signals strong enough at 50 to 60,000 feet to be 25 miles away?
Yes, so the transmitter that we were tasked with using was actually one used by Google Loon, and that's been proven by them to be able to do that. It provides a cone of reception of 40 kilometer radius on the ground, which transfers to 25 miles. So we're trying to make sure that this one point that we're circling around will for sure have a connection.
Oh, great.
Yeah, I'm not worried about that connection, I'm worried about the antenna up.
Well, so.
Yeah, I would really worry, because you have the same antenna on top and bottom, it looks like. It's gonna be a very different radio frequency going to the satellite. It's much, much further to the nearest satellite, which is probably gonna be an Iridium, which is a very low baud rate satellite, so. Just know that's not, I'm very happy you stuck with designing an airplane. But there are gonna be some considerations like command and control links and all this stuff. So plan on weight growth. When the airplane rolls out, it will not be 56 pounds. It will probably be 75 to 100. So just plan on that.
So follow up on the cellular. What you're selling is bits per second. So if you're, Google will do that, but it's emergency service and it's very few phones. So even with 4G and 5G with beamforming, the closer you are, the more bits you're gonna sell. So don't just think emergency. Think a stadium full of people who aren't getting enough bits. So the customers that I'm looking at, they care not about emergency cell phone UAV, but for large populations and also for remote locations. So, there's something to be said for being below 400 feet or above cruising altitude, but it's going to be legal to fly these things 10,000 feet, right below where they cruise. Now you've got a lot more bits that you're selling, more money.
Thank you.
Anything else, guys? Panelists? All right.
Any other questions from Joe?
Actually, so here's one, wind tunnel testing, slide 79. You said that you can't fit your wind tunnel model in the wind tunnel, got it, so you're gonna do a section. So are you just doing a 2D test?
That's correct. We're going to be confirming, because the values that we have for airfoil have only come from one source, we would like to confirm those values and stand assured that our aircraft should at least perform to those standards.
Okay. And I know wind tunnel testing is next semester, but think a little bit about trying to apply some notional correction value for 3D and for interference and all the things you know that your model doesn't account for. If you can't test it, okay, fine, but at least attempt to make a some educated guesses. Is kind of a suggestion, I guess I'll say.
Are there any equations that kind of tie the two together?
Could we
just get you close enough, maybe?
But the interference stuff is
about 20.
hard.
Is it?
So we are using some analytical methods to approximate the 3D effects at that cruise condition. So we've taken some of that into account. With the limitations of our facilities, we may not be able to derive those empirically, but with confident values on the 2D shape, we are hopeful that our 3D shape will be reflective of reality.
Sure. One thing that you could think about is casting off an attempt to do a longitudinal analysis and just focus on, say, directional analysis. So, you know, you can do kind of cut off wings, but you can still try to assess the effects of the tail, and that sort of thing. Don't know if it's a great idea, but it's an idea. So,
Page 25 is very happy to see you try to size things like ailerons, but being the source of that information, that is all like GA and turboprop aircraft. So think about, not this quarter, but next quarter, think about, based on where you're flying, how would you have to adapt your control power based on the fact that you have a very interesting shaped vehicle. Your inertias will be different than a standard Piper. How is that going to affect where you want to live on that curve?
We'll take it into consideration.
Thank you.
So like for my own education, that's just made up of, those curves are just made up of several types of aircraft that.
These are, I believe, other aircraft from senior capstone.
Oh, I see.
So
See, if you kind of,
the
see,
top
you
bar,
reference.
green bar, that is my Excel spreadsheet. So I've taken hundreds and hundreds of aircraft and tried to create very. It's not meant, there's not a 56-pound airplane in there.
And that was gonna be one of my questions, I kind of bypass it unfortunately, because we have limited stuff. But yeah, it would be good if you did say where it came from, and then say, okay, we're mitigating risk because ours is gonna fit here, and it's closer to this aircraft, just something, because you're right, it's just.
This is great for preliminary design.
Yeah, yeah.
That's what I did this for.
Yeah.
But when you get the detail.
Yeah, but then you throw rocks at it.
Yeah.
And I was gonna do the exact same thing, but I didn't know where it came from.
It's like, why am I not on that curve, or am I?
But yeah, it'd be good if you just.
And so I always go back and I say, okay, what was IXX for the airplanes that made that up?
Yeah.
Does my IXX make sense relative to what's in that paper?
But kudos for using it.
Yeah, oh yeah, no.
That's great feedback, and we'll definitely look into that for next semester.
Well, thank you for your attention and your time.
Appreciate it.
Thank you, guys.